in the sense that when you the acting on these operators, the operator, everything is operator. Operator means that I do not get results yet. I don't get the results yet. I just have operator. When you get the results, you must apply the function onto this. Now, if I directly use this equation, which means in my mind, there is nothing behind this. There's nothing behind this. In other words, let me write this down. This is very, very important, because otherwise you totally get confused. This particular term here is an operator. Until you found it's not operator, but usually this itself is operator. Operator means it has no values at this point until we have a function behind. You may not feel that significantly in this particular case. So when we finished the calculation last time, you notice that if you did not consider this as an operator, you will miss an entire term. The entire term is just coming out from the fact that when these two permute, and you will get wrong results. So that is a huge, huge difference. Now, I'm going to write down more explicitly what this means. I will show you an example, one more example to show you what will happen like this. So I'm not going to erase all of them, but I'm just erase this part. I'm going to erase this part here. So you see, in the beginning, I have nothing there. I have nothing. It's essentially this, and that gives me this value we already did last time. So that's it. But now, if the next step use the exact same function, if I put a letter F in the behind, just remember, I didn't do anything. Just here is nothing, but here I put an F over here, and this will have an extra term. This will have an extra term. It is this extra term prohibits you directly using this as a way to compute them. Does it make sense to you? So you know, this is a prohibited way to do that. Now, I'm not going to directly go over this once again. It just showed you that if you do not have F, your commutator is not calculated correctly. In a sense, how about this? In a sense that the commutator is unknown things. It's unknown. It's unknown things. Only until you apply it onto F, you will get this unknown things onto them. That's what it means. Because if you did not, you want to calculate this unknown things, so you have to apply the unknown function to start with. And then when you have unknown function applied, then you know this brackets here, the commutator, is really equal to what we said before. You see here. This is exactly like what I said here. So in other words, you have to wait until the very last minute you can do that. And this is what happens when you have these partial derivatives. Whenever you have these partial derivatives, you always have this particular problem. Essentially what you will have, for instance, if you have an x partial x like this, versus partial x like that. So that means differently. This means different. And in this case, you are waiting for the function to apply on it. You are waiting for a function to apply to it. This waiting is differently from a regular function. Just operator need to wait for something. Now these are a little bit abstract, and I fully understand. This is a little abstract. Let me show you a little bit less abstract. Suppose I have a matrix like this. Suppose I have a matrix 1, 2, 2, 3. It's obviously I have these elements. And I ask you what this value is. What this value is. You will say, you did not give me any vectors behind. I cannot tell you the value, right? This has a potential, so to speak. You have the potential to do something, but you did not tell me the vector. If I give you a vector, let's call it A and B. again, it's yes, I will be able to tell you the answers. See, in other words, this part, if this part is not there, you have to use the assuming it is there and then find it, assuming it's a generic function, and then you can find what the function that is. So this is the same thing in the sense that I gave you a matrix, but I did not give you the vectors. Tell me the answers. You say, wait a minute. You just gave me a matrix. I have no vectors. How can I get the answers? It's impossible. Because that's impossible, that's why you have to apply the unknown function in order to get this commutative. It's a little bit non-trivial, right? Any question on this part? Yeah. You just want to make sure that whenever you have this situation like this, you always use the generic way we do the calc. We always put the unknown function in the pattern. Okay, sounds good. Let's move on to the next question. Okay, the next question is that this is for the topic. What is Heisenberg uncertainty principle?
The delta A, delta B is greater than or equal to h bar over 2.
Exactly, that's that. So you cheated. All right, I should not write it. Okay, all right, okay, that's fine. All right, Cody, what are the conditions for uncertainty principle?
What do you mean by conditions?
Yeah, what kind of thing? It's not universal, right? Uncertainty principle is not universal.
Yeah, so it's if A or B, if it's A and B both equal 0, then it's because you can 100% identify. There's no uncertainty there.
What else? We have 3 or 2 or 3, right? Aisha, can you help? What are conditions? So uncertainty principle has conditions. What are the conditions?
What did you say?
Oh, I said if A and B equals 0, then it's it doesn't. That was one of them.
Yes, totally.
It has to be a quantum state, and it cannot be an eigenstate.
Exactly. So I'm going to write this down. Even though I wrote it over there, I'm going to write this down for you guys. That's very, very important. Could you guys write this down? And this is really, really important for what we are going to talk about. So Heisenberg uncertainty principle has a couple of conditions. So you have a couple of conditions, and you make sure you write this down. This is not universal. In other words, it cannot be universally in case like this. The condition number 1, A and B, these operators, they cannot be equal 0, or they have A and B not permutable, in other words. So essentially what I'm saying here is that A, B must not equals BA. So this is the condition number 1. Okay, so the operator itself has to be shaped like this. Just like x and versus px, they not equal 0, and then you have uncertainty principle that involved. That's first condition. Second condition, did you see when we do the calculation, these has expectation values. So therefore the wave functions cannot be an eigenfunction of either A or B. So they cannot be the permutable in this sense. Could you write this down, please? They are very important. So in other words, the wave function cannot be eigenfunction. If this is the eigenfunction, the other one has to be 0. Because, if for instance, if one of the eigenfunction, you got a delta A equals 0, and then this won't work anymore. All right, I think that's 2. We have these conditions. All right, I think that's it. Oh, yeah, what kind of wave function we should not use? That's we did. All right, that's it. Okay, so this is about last class, and now I'm going to use the remaining time to review the materials. Okay, so I'm going to use the different board, so that way you can, I will keep some materials on the board, so that way you will be able to see. So I'm going to review these last two chapters. It's essentially a little reviews on this part. Any particular questions you guys have for the moment? So this is a review of chapter 1 and 2. So this is the little review on chapter 1 and 2. Any particular questions that I can answer for the moment?
So 1 and 2 is just the Schrodinger equation and just the intro stuff, right?
Yes. So, yes, go ahead.
This kind of goes with 1 on the sample test. But can we go over the Hamiltonian operator and how to apply it again?
Hamiltonian operator, how to apply it. Let me go over that problem. So I just want to make sure we're on the same page. So, and which one are you talking? Do you think about a 1 or 2 or 3? Which one?
1A on the
1A. All right.
Solving part.
Oh, problem solving part. Okay,
Yeah.
good. Okay, very good. And it says that the particle box with infinite and confined eigenstate right on the Hamiltonian operator H and including the kinetic energy and potential energy operator. Okay, sure. So this is the problem 1A. The Hamiltonian operator for the particle in a box, PIB, it contains 2 parts. One is the kinetic energy, we use the T hat. The other is potential energy for the potential. So our T hat, it just equals negative H bar squared D squared over D. Here's 2m, forgive me. Sorry, wrong side. Let me erase it. 2m and dx squared like this. And this is called kinetic energy operator. Initially, we have to use a partial because it's still one-dimensional, so therefore we only have one variable. We just use a d like that. And then v here, it just equals 0. So that there's no potential. That's the infinite case. So this is a Hamiltonian operator. Any other students? Any other student has questions? Kelvin, you still have questions for what?
No, that just
That's
makes a lot more sense.
Okay, all right. Okay, so any other student has any other questions? Okay. All right. So, any other questions? Any other questions? So, if you do not have, I will just go over regularly. How about that? Let me go back to the problem solving first. Okay, so problem solving first. So, because problem solving takes a little bit of time. So there are a few things that we will quiz you on. One is, this is the problem solving, and I'm going to number them. The first thing that we will ask you guys to do, one is, of course, double equivalence. And double equivalence, how do we calculate double equivalence in this sense? Okay. And so this is the concept. I hope you still remember the equation, right? Otherwise it will be a problem. And the photon energies. Photon energy. I'm not going to write them out, but you need to remember that's photon energy. How do we calculate photon energy? So these are the concepts. And the third one is superposition. Superposition, of the wave function. And the last one is the probability density. So these are basically 4 concepts in the chapter 1. So and that's which we have. Now I'm going to start to expand these things now. So this is what we have for the conceptual part. And I'm going to move on to the next chapter, the conceptual part. So which is over here. So this is essentially it's not problem solving actually, concepts. But it's basically a little bit of calculation already involved. I think we should call it concepts. But anyway, let me use the chapter 2. I called number 5. So this is number 5, which we are going to use them. I'm going to write over here, and this is number 5. This still all the concepts. So I should not write down problem solving skills, but actual concepts. So this is number 5, and we have Schrödinger equations, and we have 2 of these. One is time-dependent Schrödinger equation. One is time-independent Schrödinger equation. So we have 2 of these, and you need to understand how we did the calculation. So in other words, the time-independent Schrödinger equation, it's an eigen equation, and it's conditional. It's a condition. The eigen equation is conditional. Do you guys still remember what the condition is for the time-independent Schrödinger equation? Tobin, do you remember that? What's the condition for time-independent Schrödinger equation? You know, from time-dependent Schrödinger equation to time-independent Schrödinger equation, they're not the same thing. So what's the condition, Cody, to get a time-independent Schrödinger equation? From time-dependent Schrödinger equation to get a time-independent Schrödinger equation, what is the condition? Isaac, can you help?
Is it the Hamiltonian?
Exactly. Hamiltonian is
Independent of time.
exactly. Did you hear it?
Oh, okay.
Did you hear it? So in other words, that's the key. The Hamiltonian should not depend on the time, like this. And then you will have a stationary state evolution. So then you have stationary state evolution. Stationary state evolution just means that if you have a time independent Schrödinger equation, solve it, and you have eigenstate, that's a t equals 0 here. And then the time dependent part, the stationary state evolution, will be 5t. I ignore the r now, position operator. And this will be equals e to the negative I e n h bar, t over h bar. Sorry, my font size is a little too small. Minus I e sub n t over h bar. And that's stationary state evolution. Now this can be joined together with the superposition. You know, if superposition comes over here now. Superposition is going to be utilized here. So superposition, which means the following. If we have a state which is in a mixed state, so let me save my time. If you have a mixed state, which means like this, phi n cn, and this is a mixed state like this. So it's not just eigenstate, it's a mixed state. If the t equals 0, you have this expression. Now if the t not equals 0, once it is in the eigenstate, it will have the similar shape like what we have. Essentially, if this is t equals 0, then you will have this fast factor again, e to the negative I e n t h bar, like this. And this is just come from the superposition principle. You can add these principles up, and that's the superposition operators. So that's the stationary state evolution. And so when you have superposition, so state evolution will evolve like this shape. From this, now we can calculate a little further Number 7 is expectation values. And so this way you need to look at the homework assignments. The homework assignments must be reviewed extensively, with expectation value for the homework side of it. So we assign homework and also quizzes as well. So that's one which we have. And including some concepts in the quiz. But expectation value, you must know how to do it. For instance, if I have a wave function like this, suppose my operator is called O, then my expectation value is going to look like this. So this is going to be my expectation value, and this will be something like this. And we will have one problem for you guys to solve like this shape. Almost identical to our sample, but a little bit more convoluted. For instance, if I want to calculate, let's say for the particle box, I can directly use this equation to do that. So that's what you need to know. And in order to calculate this, and you need to remember you have multiple terms. For instance, if I have 2 terms, if you multiply them out, you can have 4 terms comes out, and do the calculation in this format. So, and that's called very basic expectation values. So that's needed. Are we good so far? So far so good? Okay. If you have a question, just stop me. All right, sounds good? So that's expectation value. In other words, we want to know how to do the calculation. And when you finish reviewing this part, the main thing that you need to remember is the homework and the quizzes. These are the key part. We won't exceeding that too much in a sense. And so this is for the essentially conceptual part more than problem solving skill. I think I should change this. Folks, change this to concepts. Okay. And now we have a problem solving, which is over here. We will ask you to solve one particular problems. And you've probably seen this before, but not necessarily exactly the same. So this is a problem solving. Problem solving. So how do we solve these problems? And one problem solving we will use is a similar problem like in our particle box or quantum wells. For instance, if I have a quantum well, suppose I have a quantum well, I won't be asked you to compute all of them. It's impossible. It's just a small portion of that it is possible. For instance, I could have a quantum well look like this. So this is a quantum well in this particular format. And I will ask you to calculate some small portion of this problem. For instance, this is the region 1, this is the region number 2, and this is region number 3. And this is exactly the same as our sample test, sample exam, exactly the same. I will ask you to calculate the boundary conditions, find the boundary conditions, use the boundary conditions to link the wave function phi and phi 2 like this. So that's the quantum well. And this will be directly computed in this format. Okay. So that's our boundary condition problem, and we will quiz you whether you know how to connect these wave functions. And one thing that is very important, what about the wave vector k? How the wave vector related to E and V0. So this is the V0 here. How these two are related to each other, and how Q is related to E and V0. So these are very basic ideas, which means we have this one here, and you must remember the quantum well is a localized state, and state in infinite is going to drop to 0. Here is drop to 0, and here the finite is between these two regions. That you need to remember that. So how these two relate to each other. Number C, K and Q relations, how they relate to each other. So how these K and Q are related to each other on one particular problem, and that's we want you to understand. This is the quantum well problems. For the infinite particle in a box, for the particle box, we will mainly quiz you use these calculate expectation values. Folks, could you guys write this down? So particle in a box, we will ask you to calculate this. So in other words, the wave function is a little simpler, so we will ask you to calculate expectation value for this. While the quantum well, the wave function is slightly complicated because I have to tell you A and B, all of those ones. And A1, A2, A3, it's very long equation to write, so we won't quiz you that. But the particle box will ask you to calculate expectation values on this. Okay. And this includes time evolution on this, so that's why I didn't mention. So sometimes we call it concepts, but in this case, it's actually a small calculation, just a particle box, similar like our sample exam. Does it make sense to all of you? Make sense? Can I get a thumb up, everybody? Okay, good. So that is that's the equation which we want you to emphasize, and this is almost 100% will be on the exam. So there's no other things, and then you ask you to calculate a few things, and here it's just a partial problem. Now it's just remember partial problem. We won't ask you to calculate entire things because that's just way too much, and so this is the quantum well. And then we just ask you to derive some equations, and so I just check my time, how much time I spend on those ones, and then you will probably have a similar amount of time. And that's number one. Number two, this will be tunneling. So this will be tunneling. Tunneling, we ask you a few questions, also similar like we did before. So just remember, tunneling has different questions asked. So we have a wave comes over here and asks you to calculate tunneling. And you remember this, here's A and here's a B. Now the wave function in the tunneling are different from the quantum well. Quantum well, these are the all bound states, and these are the continuous states. Just remember, they are different. So let me write this down. This is continuous state. Or sometimes we also call it traveling state, because it really travels. State. So the energy is the incident energy determined by the incident particle. So that's why we did not normalize it in this fashion. So that's quantum tunneling. And now quantum tunneling, remember the wave function in the region number 1, 2, and 3. And these three regions are different. For your homework problems, you only have 2 regions, but in this case, we have 3 regions. So regular tunneling, the first region, phi 1, and it has 2 terms, e to the I kx, plus reflection, negative to the I kx, like this. So 1 is into that, and 1 bouncing back. And then in the middle, in the middle here, and that's a different. So this, you have a decay. One is the, so we usually have to use the letter Q to represent that. So, and you will see A, e to the positive Q, and B to the negative Q like this. So the ones go this one, go that way. And you can also determine which one you want. So, and you can determine the results. So that is what we have here. And then finally, the region number 3, and this is the transmit. We use letter T to represent that, e to the I kx. And we ask you, well, something like this. You will ask you about something like R star, and this is denoted by a capital little R, and transmission T star, and this will be utilized. So essentially, and we will ask you T plus R, and this is going to equals 1, and so that's transmission. And relation between transmission coefficients, in other words, how, and this will be a smaller problem in a sense, so this is going to be a smaller problem. How these two are related to each other, how the T and R relate to each other. I don't want you to remember all the equations, but I just want to know how we get this relation. How to get the relation. Second, the dependence of P and R on the potential E and the energy E, and the width of the well. In other words, if this width of the well. Essentially, we want you to remember the general features of these three waves, and this is in the textbook. You need to check the book and check the book how this wave actually evolves. And you remember that if my A's becomes bigger and you have dropping of the transmission coefficients, reflection is going to be increased in this particular format, and that is basically on the tunneling. So these are the problem solving here, and of course so left part is a conceptual part. Oh, folks, could you add one more thing? I forgot over here. Some quantum ideas we want you to remember. And I would definitely will quiz you guys. We'll quiz you 3 times, all right? Twice in the quiz. And what is a quantum, what is a quantum state? And this will be 100% there. Please give me good answers. What is a quantum? How do we describe them? And what way we describe them? So that's the... And you remember how many different ways? We have at least 2 different ways, right? One is what? One way we describe a quantity using the Schrödinger picture. What the Schrödinger picture is basically about? He's using wave functions. What about Heisenberg's idea? What about Heisenberg's idea? Matrices, exactly. Matrices are vectors, eigenvectors, like these vectors. And then the Dirac used these notations, in the brackets notation. Yes, angle brackets, these notations. He's just representing all of those different pictures in his notation, make things a whole lot simpler, like this brackets coming out like this. Yeah, make sense? Any other questions? And and again, the emphasis is on homework quizzes. You must review all these quizzes and homeworks. Okay. If you did not review or did not do it correctly in the first place, you must make absolutely sure you go over them completely. And one last thing, what I will do, number 3, and you make sure you have your formula sheet ready. With the formula sheet ready, and you're allowed to use 2 formula sheets if you wish. One thing that I strongly recommend you, if you have a book with you right now, yeah, folks, you can look at our textbook in the preface. In the preface, if you're under there, preface has table 1. Yeah. Preface table 1. Yeah, preface table 1. I think page 11. So the capital, the Roman number X1, like that. X1. Yeah. Table 1. Are you on the table 1? It's in the preface. Can you see that? Okay. Are you there? Cody, are you there? Okay. Did you see chapter 1 key concept? Did you see that? And that's how you review them. In other words, when you review the materials in class, and this is what we want you guys to remember. For instance, first chapter, energy, quantum, degree, wavelengths, and wave function, all of those ones you see, measurement expectation value. So, and then you also look at the key formula. Did you see the first key formula is our the photon energy formula? That's what we used. And then you can see probability densities and rho, all these operators. So that's what and that's why we write these books ourselves. We have a lot of flexibility. That's why I think this is much better. So then the second chapter, you see the electron Schrödinger wave functions, Schrödinger equations, and quantum wells and barriers. And you also see this master equation. Do you see the master equation in the chapter 2? Did you see here? Eta equal plus minus omega cosine eta. Did you see that? And you also see another master equations in the similarly in this format. You can write them down. And tunneling, did you see tunneling? So that's the tunneling coefficients. So in other words, if you forget anything but this small table, you should remember them. All right. And that's almost, of course, it cannot include everything, but it's almost the pinnacle portion of that. So essentially, when you close this book, you at least okay, I remember this. These basic things. How do we do that? And when we list this table, actually, it took us a while because we want to make sure which one is equation should be there, or which one should not be there. So that's why, again, in this particular table, I want you to put them in your formula sheet somewhere. In the formula sheet somewhere, you must make sure to put a formula. You cannot use a book for the exam, but you can put it in a formula sheet. Okay, so that's the key. And that's why I like our book in the sense that when we iterate a couple of times, we found it's better. And this will be the same for the later chapters. You can see for our harmonic oscillator, you can see nuclear vibration, the commutation relation of position and moment. So this whole bunch of things is actually utilized in similar fashion. So, all right. Any other question that I can help with? So we have about 10 minutes remaining. Any other questions? In the meantime, and here's the thing. Once you're done with this formula sheet reading, and during the Saturdays or Sundays, if you still have questions, I told another class, they also have some things. I will about every 2 hours, I will check my emails for you guys. If you guys have questions. What I will do, I'll do the following. Let me call it number 4, down over here. If your question is long, for instance, you prepare for this, your question is long, very complicated, what I will do, I will create a video for you. I will create a video for you because that way it's much simpler to explain. In other words, you say, Dr. Zhang, I have this particular question, I want you to explain what that is. If it's complicated, if it's not complicated, I just simply put them. So that's A. B, I will put it on a discussion board. Everything will be under discussions on the campus. In other words, everything will be under discussions. I will have an item called exam number 1, and you can post a question there. I will answer them. If the question is too long, I will use the videos. Sounds good? Sounds good? This way that I want to help you as much as I can. All right. Any other questions? So we have some extra time. We can work on what we left over last time. So if it's not the case, we're going to work out some additional materials today. So besides our preparing for the class, so we're going to go over what we left over this time. So I'm going to show you over here, and we're going to start with what we left over last time. All right, so I'm going to erase this now, and this time we are going to move on to section number 2. So section number 2 is the harmonic oscillator, and I realize this is going to be the most complicated chapter so far, or section so far. So I'm going to go over real slowly. So this is the section number 2, harmonic oscillator. So this is the harmonic oscillator, and for the chapter number 2. It's kind of interesting. We will actually use the same thing like this as your 311 like this. So almost identical for that. It's an oscillator in that particular format. I'm so glad to see that. Okay, let me show you what this thing's all about. In other words, what we are going to describe this. So anything in quantum mechanics, we always start with the Hamiltonian. So this is the Hamiltonian for a harmonic oscillator. And we're going to start with the classical Hamiltonian first, and then move on to the quantum Hamiltonian. So classical mechanics, I use letter CM to representing that. The classical Hamiltonian has H equals KE plus PE. That's the classical Hamiltonian written in the following way. We're going to treat just one dimensional, by the way. So this will be essentially kinetic energy will be P x squared over 2m plus 1/2. Now, usually you have spring constant kx squared, and did you guys use a k? Yes, you didn't use a k like this. Yeah, you use everywhere a k. That's very good. And now this k is not the best way to use them, so we would change this k to m omega squared x squared. And the main reason is the following. Classical physics, this part is just spring constant itself. And here we have omega. And we can get ready for the quantum mechanics. Now the quantum equation look like this. H is going to be h hat. And then the kinetic energy becomes T hat. Potential energy becomes V hat like this. And this equation is almost identical. So from here to there, which we call the quantization of the system. You quantize the Hamiltonian first, and then get this equation here. Now the kinetic energy originally is P sub x. Now you will become P hat sub x over m, like this. So that's the kinetic energy. The potential does not change because in the position representation, x still x. P just becomes part negative I h bar, partial T. So that's the difference. So second term does not change. So in the quantum, we have this situation like this. And that's what we learned. If you look at the textbook, they always present this. And when we were writing this book, we found something very interesting from Dirac's book. I read Dirac's book many times, but I do not. But once we started writing this book, and when we read Dirac's book, something reveals to us very interesting idea. I'm going to show you his wonderful idea. Let me show you an extremely simple equation. Dirac had this idea. A x squared plus y squared. These are just classical numbers. It's nothing fancy about this. And equals a star. And Dirac's question is very simple. Did you have a square like this? Did you have a square like this? Let me put an a for the moment. Let's put an a over here. Let's put an a over here. Now I'm going to take square both sides. And I'm going to put the square root both sides. His question is this. X squared plus y squared, can I write them in the following format? Can I write in the following format? Can I write a C multiplied by A plus without N, just A plus B. His question is square root of something can I written in the format of A plus B? Or can you make them A squared like this? This, of course, different A's. Let me just call it C squared. Doesn't matter. So I didn't understand the logic. It's just like a mathematical game, like play this. You did not see anything involved. But when we are preparing for this, and it struck me immediately. My goodness. His equation here, watch carefully. You watch carefully. He literally doing this guys here. He literally doing this ones here. He literally doing this one here. In other words, he's doing like this. He wants to both sides somehow take square root of these operators. That's what he's doing. And then it reveals me to immediately. It turns out, did you see I have a square root like this? Did you see I have a square root like this? It turns out the key concept really proportional to something which we don't know yet. Let's call it constant C. And because these are, did you guys see it? These are the operators. Did you guys see these are operators? It's not regular numbers. So therefore, you will see something like this. In other words, conceptually, he was thinking, can I take square root any operator like this? Become C dagger. And then when I look at this, oh my gosh, he's on the right spot. This is exactly what you will see. In other words, next class you're going to see me to write something like this. Watch carefully. Did you see this guy's square root? It just have A there. Now, if I square both sides, that A has to be squared, right? Because both A has to be squared. Essentially, you will see me in next few classes. We will do something like this. Now, when you both square it, because all these operators has a complex, you will see me. We will convert this guy from a dagger, another A. So that's so beautiful was that this is in the Dirac's book somehow loaded it in this particular equation. What he was doing, just take square both sides. This should not have square. Okay. Essentially, what this is, what he was doing like this. Essentially, what he's doing like this. And then this equation, in other words, you just want to take square of both sides, and then you get this equation. And I keep on reading his book, and I realized, oh my goodness, what he was trying to do. You guys remember, Einstein had this equation, right? P squared C squared plus M C4 like this. He has Einstein had this equation. Did you guys have square root over here? Did you guys have square root over here? He was thinking, can I take square root of this guy with the operator in that? This will become operator now. I'm not going to write. This become operator. Can I take square root of this? When he did it, then he created relativistic quantum mechanics. That's what he got a Nobel Prize for. Essentially, Tobin, if I tell you, take square root of this guy, get an expression like this, this gave you a Nobel Prize. That's why Niels Bohr told that Paul Dirac was the strangest person ever. He was trying to do this. Take square both sides. I want to have expression like what I just showed you there. When I read his book and later on I realized, my goodness, this was actually doing the same thing. Essentially, I take square root both sides. Originally, square root, if you take square root both sides, it's not easy, right? Because when you can't think about this. If you square both sides, you have a squared plus b squared plus 2ab. Right? Then this left-hand side, x squared plus y squared. Now, if you let x equals a, b equals y, what happens to ab? What happens to the ab? You know, if x equals a, y equals b, but what happens to the ab? And Dirac has a wonderful idea. You can eliminate AB if you introduce a matrix. That matrix is electron spins. It was so insightful. I read many times of these books, but I never understood it until when we will prepare this part. And something jumped to our mind was that, oh, this was the same trick actually did. The same trick later on promoted us to invent something interesting was that suppose I have one single matrices, A, just a matrix, times another itself, same matrix, equals to identity matrix. In other words, A times A equals identity matrix. What is this A? You understand my question? A equals A times A self equals this matrix. What is this A? Then I realized, oh my gosh, that's so beautiful. Why? If you do this is very simple mathematics, right? It's just like A. We don't know the value that is. You have a value like A, B, C, D. We don't know A, B, C, D. You just called A equals A, B, C, D, 2 by 2 matrix. You square this guy, you get this matrix. You find out what is A, B, C, D. If you're done with that, this becomes spin matrix. This becomes spin matrix. I never saw a book did it, but I got some idea from Fermi's lecture notes. Fermi does not have this expression. He mentioned it, but did not go through it. And when I look at that, and one day I was just sitting in the office and said, can I do something with these matrices? And I just play with it. When I'm done with it, I was so happy. I said, my God, these two actually same thing. That's why Dirac takes square root here, and I did a square there. Did you see this is square root of this? I did a square there. They actually connect to each other. So then the entire mathematics and physics, oh my gosh, it's just beautiful and beautiful. And this will be in chapter 7. So if you guys cannot hold on, I can show you where that is. Could you guys turn to? Let me show page number. This was so interesting. Okay, on page 167. Page 167. Let me write this. I showed that the equation 6.6.1. 6.1.1. This is on page 167. Page 167. Yeah. Equation 6.1.1. And that is what? Did you see the 2 by 2 matrix? And I quote the Fermi's written there. And A squared, and that's just a Pauli matrix. Oh my gosh. And I was thinking the mathematics is so beautiful. I just said, wow. So in other words, you see, sorry I trapped a little bit, but you can see the logic is actually the same thing, but I just do it twice like this. How do you like this? How do you like it, you guys? This was essentially so elegant, and I was, oh my gosh. In other words, next class you're going to see me, in some sense, boring, which is I'm going to prove this guy's here. It just takes square root of both sides. All right, let me end it here. Okay. Any other questions? And again, I will grade your homework, and I will turn in. Maybe I don't know how long it takes. When I done it, I definitely leave that in your mailbox. Sounds good? Sounds good? Okay, very good. And I will post the key there in the